All right, let's rock a Pythagorean theorem related rates problem. Let's see how that comes into play. The top of a 15-foot ladder that is resting against a wall is suspiciously pulled away from the wall so that the top of the ladder falls at a rate of 2 feet per second. So imagine you got like a ladder like this and it's going, and as it goes, right, the base of the ladder here is going to go away from the wall, and this is going to come down like that. So let me draw a picture of what's going on there. So you've got a wall, and you've got a ladder, and I guess I'll just put the ladder up at the top of the wall here, and we'll make it dotted, like a hypotenuse of a triangle. I'm going to put a 15 in this diagram because the ladder is not changing, right? It's not an extension ladder. That'd be cruel. And then you've got the things that are changing in this. I like to put down the variables that are changing. You saw that in the cone video problem. So what's changing? Well, again, the distance that we are away from the wall, this part right here, that would be changing, right? As well as the height of the ladder along the wall. So we'll call that y creatively for, the y-axis, and then x creatively for the x-axis. So that's changing. So it's being pulled away from the wall. So we're going in that direction right there. And we're told that the top of the ladder falls at a rate of 2 feet per second. More on that in a little bit. We've got an equation we can now relate. So how do we relate lengths of we're going to assume that that wall makes a right angle, most problems do, with the ground. How do we relate legs of a right triangle to a hypotenuse? The Pythagorean theorem. So we use that geometry relationship that I'm always talking about with related rates. You get x squared plus y squared equals 15 squared. Now, as always, we're going to look both ways to see, can we take a derivative? And if we can, do it. If not, don't do it, and we'll have to solve for one variable in terms of another. So I look at this and I think, well, the derivative of that with respect to time, that's not so bad. I can do that. And the derivative of this with respect to time, yeah, that's not bad. Let's do it out. I think the derivative is pretty clean here. So the derivative of x squared with respect to time is 2 times x times dx dt, right? Or times x prime of t, if you prefer that notation, plus 2 times y times dy dt, or dt, equals the derivative of a constant. Even though it's 15 squared, it's not 2 times 15. The derivative of a constant is 0. The ladder's not changing, so the rate of change of the ladder's length should be 0. It makes sense conceptually as well. All right, so now, as we've done in the past, we're going to take stock of what we have and plug in what we have to find out what we don't have. So we're told that the ladder falls at a rate of 2 feet per second from the top. That would be dy dt. And the reason why that is, again, it's the change up and down. It's falling at that rate, not being pulled. And you're being asked, how fast is the base of the ladder being pulled? So we'll get to that in a second. So this would be negative 2 feet per second because it's going down, right? That's important. Then, what else do we have? We have x. Well, do we have the x amount? When the base of the ladder is 12 feet from the wall. Oh, that would be the x value. So the instant that the ladder is 12 feet away, got it, the base of it, that would be this, would be 12. So we've got x, so let's just plug it in, 2 times 12. We don't have dx dt. That's okay because we're being asked, what is the rate at which the ladder's being pulled away from the wall, the base of it? It's good that we don't have that. Plus 2 times, we don't have y. We've used all the numbers in here. Dy dt we do have, that's negative 2. Okay, and that's equal to 0. So we need to find the value of y, because dx dt is fine that we don't have it. That's what we're being asked for. But y, there's got to be a way to find it, or else we're not going to be able to solve this problem. And this is how I know that we need to go and find y. Again, I don't like to list things out, memorize it, and say this is that problem where I need to find y. This is the problem where, oh, I've got a missing variable that I don't have the luxury of having missing, so I got to go and find it. Or luxury of being missing, I guess, is proper grammar. So how do I find y? Well, I'm given x. I don't have y, and I have the 15 squared. So I'm plugging in 12 into the original equation and using it to solve for what the y value is. It's the Pythagorean theorem. So if you notice it's a Pythagorean triple, 12, another number, and 15, then great. If not, no problem. So this will be 144 plus y squared equals 225. We subtract 144 from both sides, just solving like normal. And so that's going to be 225 minus 144 is 81. And the square root of both sides will yield us y. So y is equal to 9. Well, now that I've got y is equal to 9, I can insert that back into the equation, right? So now y is equal to 9. Plug that in there. Now we've got all the variables we needed, and we just need to solve for the unknown of dx dt, the rate at which we were pulling this ladder away from the wall. So we simplify a little bit. We get 24 right here, dx dt, oh yeah, plus 2 times 9 times negative 2 is negative 36. It's equal to 0. We add 36 to both sides. Very easy equation at this point, right? It's just a number times a variable is equal to 36, and divide by 24 on both sides. Dx dt is equal to 36 over 24. We can reduce that down by dividing numerator and denominator by 12. That'll get us 3/2. Now our units are a change in x, which would be feet, per second, right? Because it's per time, dx dt, and the time that we were talking about is in seconds. And that's your answer. The thing to note here is that x of t, or dx dt, should be positive because it's getting pulled away from the wall, right? So it's going in the positive direction. We're gaining distance from the wall, not losing it, right? And that's why we have a positive dx dt. All right, I'll end it there. A classic problem yet again. You can rock this one, no worries at all now, right? Right.